Good morning. My name is Jérôme Delporte. I work at CNES, the French Space Agency, and it's a real pleasure to be here this morning for a talk on our recent work on absolute calibration of GNSS reception chains. My co-workers here are Thomas Junique and François-Xavier Marmet from our radio navigation department, and David Valat, who is the head of the our timing laboratory. Part of this work has been carried out in the frame of the DIMITRA contract, which is part of the H2020 program funded by the European Commission. And if you want to know more about the DIMITRA contract, you can attend the presentation by Patrizia Tavella tomorrow afternoon, I think. So this is the outline of my talk. First, I will briefly recall why we need absolute calibration. Then I will present our calibration technique at CNES. Then I will show our recent improvements and results, and finally, I will give some conclusions. So, as you know, the GNSS measurements are referenced to the GNSS antenna phase center, which is good, but which is not what we want for comparing clocks. So, if you want to refer to the local clock, you need to know the delay between the antenna phase center and your local clock. And for this, you need an absolute calibration. You can also do a relative calibration, provided the traveling station has an absolute calibration. So at some point, you need an absolute calibration for time transfer. Another application is for GNSS. You know that each GNSS provides the time offset between its own system time and a reference UTC in its navigation message. For instance, GPS broadcasts GPS time minus UTC USNO. If you want to determine or to monitor this offset, you need a GNSS station connected to a UTC-K, USNO for instance, for GPS, and you need also to accurately determine the electrical delay between your antenna and your reference clock. So you need also an absolute calibration. So in absolute calibration, it means you have to determine the absolute delay between your antenna phase center and your local clock. And in the absolute calibration, you determine the delay of each element individually and independently. That is the antenna cable, and the receiver itself. So how do we do that? For the antenna, we use an anechoic chamber and a vector network analyzer. I will come back to this in a minute. For the antenna cable, we could, well, it looks like the easiest element to calibrate in the chain, but you know, the devil is in the details. One could imagine actually many different techniques to measure a cable. And it's not the purpose of my talk today, and I will refer you to a very good article published by Daniele Rovera and his team at Observatoire de Paris, in which he compares 5 or 6 different techniques to measure the electrical delay of a cable. And last but not least is the GNSS receiver itself, for which you need a GNSS simulator that provides GNSS-like signals. So let us now focus on the calibration of the antenna. So this is the way we do it. So we have a transmitting antenna connected to one port of a VNA, and we have the antenna to be calibrated connected to the other port of the VNA. This is a picture here of our transportable anechoic chamber. So as you may see, we have 2 cables in red here, C1 and C2, and if we connect these 2 cables before the measurement, we have a tear measurement, which is very good because it allows us to measure any cables. So it's very good for the uncertainty budget, which is reduced, and it's also more simple. So all you need to know to calibrate your antenna is the delay of the transmitting antenna and the distance between the transmitting antenna and the antenna to be calibrated. The transmitting antenna delay can be determined using triangulation method with, for instance, three antennas that you measure 2 by 2, and at the end you get the delay of each antenna. And then you use one of them for measuring your antenna. So this is an example of result that we obtained recently for 2 GNSS antennas from Aero Antenna Technology. One is here. So more important is the uncertainty that we got in the end, which is for L1 band and L2 band in the range of 0.5 nanoseconds. Now, if we move on to the calibration of the receiver, as I said, we need a GNSS simulator that provides GNSS-like signals free of any atmospheric effects or multipass effects. And to put it in a nutshell, the receiver internal delay is simply the difference between the pseudo-ranges measured by the receiver minus the pseudo-ranges provided by the simulator. So this is this blue term, RXR minus SR, this difference of pseudo-ranges. Of course, you have to correct for a certain number of things, in particular, the simulator delay here in green, the SD, which needs particular attention. So this simulator delay is actually the time delay between the 1 PPS rising edge of your 1 PPS output of the simulator and the start transition of an amplified GNSS code. You can measure this time delay with an oscilloscope. Here it is an example with a GPS 0/8 code. For this, you need to put your simulator in a single fixed satellite mode. And then you can determine the simulator delay either by directly reading on the screen your time offset or by post-processing the data using a correlation software, which is deemed to be a more accurate method. We developed at CNES a new correlation software recently, and it now covers all GPS, Galileo, GLONASS, and Beidou codes. I have also to say that here the transition is quite obvious for GPS C/A, but for some GNSS codes, in particular for some Galileo codes, the transition cannot be easily identified on the oscilloscope. And in these cases, you really need a correlation software to get your result. The sole drawback of the correlation software is that you cannot use it for the GPS P code because the length of the GPS P code is 1 week, and therefore you cannot correlate. So we calibrated 4 receivers, which were 4 Septentrion Polar RX40R Pro receivers with 3 different simulators. These simulators are a Spirent 6700, a Spectracom GSG6, and an Avis Legacy. And in this table, what do we have? In fact, we have the difference. You remember that when we calibrate the receiver, we compute the difference between the pseudo-ranges of the receiver minus the pseudo-ranges of the simulator. Okay? So if you compute that for C1 and for E1 and make the subtraction, this is what we have in this table. And what is interesting is that very often we got simply 0. Except for the Avis Legacy simulator, which value is close to 0, and it's, well, let's say consistent with 0 at 1 sigma. It means that the simulator delay for C1 minus the simulator delay for E1 is the same, whatever the simulator, which is a bit weird because these are 3 different simulators from 3 different manufacturers, and so there is no reason why we would have the same simulator delay difference. A reasonable assumption for this is that, in fact, this difference is 0, which means that the simulator delay for C1 and E1 are equal. Under this assumption, if we use simply this equation here, we get that the internal receiver delay for C1 is equal to the internal delay of the receiver for E1 with an uncertainty of 0.5 nanosecond, at least for the 4 Polar RX40R Pro that we tested. We did the same study with the C1P1 bias using two simulators, the GRG6 and the Spirent 4760, and we arrived to the same conclusion. That is that the internal delays for C1 and P1 are equal at the level of 0.4 nanosecond. An important point also is that the fact that the simulator delay for C1 and E1 are equal is also a good indication of the calibration quality. And I must say that we got the most consistent results with the Spectracom simulator. That's why we use this simulator in the rest of the results I will present. So we decided to calibrate two complete chains, that is two antennas, two antenna cables, and two receivers. These are chain A and B, and these are the uncertainties that we got for the complete chains for P1, P2, and E1. So we have uncertainties, 1 sigma uncertainties in the range of 0.6 to 0.9 nanosecond, 0.7 to 0.9 nanosecond. And the contribution of each, the order of magnitude of the contribution of each element is given here. So as one would expect, it is mainly driven by the uncertainty of the calibration antenna and also by the receiver. So with these two complete chains that were calibrated in an absolute way, we did the validation campaign in common clock configuration with a short baseline, using this time real signals, not simulators, using real signals. And so these two chains work in parallel, and then we compute simply the difference of the measurements from chain A and B, each chain being corrected by their own delays. And so obviously we should get 0 if we have been working properly. So this is what we obtained. So here it is 0. We have 1 nanosecond per division, and we computed the difference of the two chains using two different approaches. The first one is to compute the CGTTS file and then to make a common view. So these are the results in red. And the second approach was to carry out direct difference of the pseudo ranges, which can be done since the baseline is very short. Of course, and these are the results in blue. So the two approaches agree quite well as expected. Of course, the blue uncertainty is much bigger because of the noise of the code. And so this is what we obtain, and the question is to what extent is it consistent with the validation, with the calibration results. So the uncertainty of the calibration that we have to take into account is in fact the root sum square for each observable, the root sum square of the uncertainty of both chains. And this is represented here by these black boxes. And therefore it means that our absolute calibration results are consistent with this common clock validation campaign at 1 sigma. So we were quite happy. So to conclude, I would say that we presented the absolute calibration method and some results. We developed a new correlation software that covers all GNSS codes. We observed that for the 4-polar RX40R Pro we tested, we should have equal receiver delays for C1, P1, and E1. And quite important, the overall uncertainty for a complete chain for a given code is in the range of 0.7 to 0.9 nanosecond at 1 sigma. Our future goals are, of course, to further reduce the uncertainty budget, to improve the simulator delay determination, and obviously to extend to other GNSS codes. I guess at the end of my talk. Thank you very much for your attention.